So if you take 2a square common, then this will be root of 2a into bracket 1 plus cos of phi 1 minus phi 2. Yes. So this can be the expression for the two SHMs with same amplitude but different initial phases. But if the initial phases are also same, if phi 1 is equal to phi 2, then phi 1 minus phi 2 is equal to 0. Cos of 0 is equal to 1. Therefore, a is equal to root of 2a into 1 plus this will be under root. As we take root of 2a square common as root 2a under root 1 plus cos of phi 1 minus phi 2. So this will be under root 1 plus cos of 0. So a is equal to root of 2a into root of 2. Cos of 0 is 1, 1 plus 1 is 2, so root of 2. So a is equal to twice a. So this becomes a maximum amplitude. So for composition of two SHMs having same amplitude and same initial phases, the resultant of the amplitude A max will be plus or minus twice A. But if the phase difference between the two initial phases phi 1 minus phi 2 is equal to pi by 2, means one of the particles starts its SHM from mean position, but the another SHM, its initial point is at extremity, then the phase difference between both of them will be pi by 2. Then cos of pi by 2 is 0. Then the expression will become a is equal to under root a1 square plus a2 square plus twice a1 a2 into 0. So this will be root of a1 square plus a2 square if the amplitudes are different. But for a1 is equal to a2 is equal to a, this will be under root 2a square. So it will be root 2a. If one of the SHM is starting from mean position whereas the other starts from extreme position, and the condition if phi 1 minus phi 2 is equal to pi rad, means one particle starts from one extremity, other particle starts from other extremity. So this SHM is from starting phase is from left hand side, and for this starting phase is right hand side. So the phase difference between them is pi. There the amplitude becomes under root a1 square plus a2 square plus twice a1 a2 cos of pi. So this will be a1 square plus a2 square, cos of pi is minus 1, so minus twice a1 a2, and so this can be written as a1 minus a2 the whole square. So a will be equal to a1 minus a2. So this will be the minimum amplitude for such composition of two SHMs. If A1 is equal to A2 is equal to A, then in such case the amplitude becomes 0. A1 minus A2 will be A minus A is equal to 0. And so in this way, when the two SHMs take place simultaneously, the resultant amplitude, the resultant displacement is given by A sin of omega t plus delta. Capital A is the resultant amplitude, and we get the expressions for resultant amplitude for various initial positions. Our consideration is A sin of delta is equal to A1 sin of phi 1 plus A2 sin of phi 2, and A cos of delta is equal to A2 cos of phi, A1 cos of phi 1 plus A2 cos of phi 2. If we divide equation 1 by equation 2, then A sin delta upon A cos delta, this will be equal to A1 sin of phi 1 plus A2 sin of phi 2 upon A1 cos of phi 1 plus A2 cos of phi 2. So A cancels with A, sin delta upon tan cos delta will be tan delta. So this is A1 sin of phi 1 plus A2 sin of phi 2 upon A1 cos of phi 1, A2 cos of phi 2. And so the resultant starting phase delta for the compositions of two SHMs in a resultant displacement, delta is given as tan inverse of A1 sin of phi 1 plus A2 sin of phi 2 upon A1 cos of phi 1 plus A2 cos of phi 2. Yes. From the given expressions, we will come to know the value of A1 and A2, and knowing the value of phi 1 and phi 2, we can obtain the values of sin phi 1, sin phi 2, cos phi 1 and cos phi 2. And so as we get the angle over here, tan inverse of the given value in radian, we will be able to get the initial phase delta. And so this is all about composition of two SHMs. Now, the next article we are going to study is energy of particle performing SHM. consider a path AB on which the particle is performing linear simple harmonic motion with O as the mean position. So particle oscillates about the mean position O. As the particle gets displaced, and reaches the point B, let x be the displacement of the particle with respect to the mean position. Now in this case, there will be certain linear velocity acquired by the particle when it is moving, say v. If m is the mass of the particle, then certainly it acquires certain kinetic energy. And so here we get the expression for kinetic energy as 1/2 mass of particle into square of the linear velocity. 1/2 mv square. Now at any point P, if v is the velocity, then the velocity can be given as v is equal to omega under root a square minus x square. If the particle is moving toward the positive extremity. But at point P, if the particle is returning back from B and if it is moving towards O, then the same velocity will be minus v. So irrespective of the direction, whether it is going toward the right or toward the left, at point P, the magnitude of velocity will be v is equal to omega under root a square minus x square. And so, if we put this value over here, we come to know that the value of v square becomes omega square in the bracket a square minus x square. And so kinetic energy Ek, this will be 1/2 m. Now for v square, we can write the expression as omega square in the bracket a square minus x square. And so the kinetic energy at point P is 1/2 m omega square a square minus x square. So this is the expression for kinetic energy of a particle performing simple harmonic motion at any point P on the path AB, where the displacement of the particle is x. Now in such a case, we can also have the various conditions. Condition 1. Kinetic energy at mean position. O. At O, x is equal to 0. Therefore, Ek at mean position, this will be 1/2 m omega square a square minus 0, because x is 0, 0 square will be 0. So this becomes equal to 1/2 m omega square a square. And so when we consider the mean position. At mean position, the kinetic energy is given as 1/2 m omega square a square. Now, let us consider the kinetic energy at extreme position. So Ek at extreme position, either at A position or at B position. So at extreme position, the value of x is equal to A. At B, x will be equal to A, or at A, the magnitude, the amplitude is A. And so this becomes equal to 1/2 m omega square A square minus the value of x is A, so it will be A square. So A square minus A square will be 0. So this will be 1/2 m omega square into 0. So value comes to be 0. So kinetic energy at extreme position will be 0. And so here we see that the kinetic energy at extreme position, say at position A or at position B, will have 0 value, 0 joule. At mean position it will be maximum, it will be 1/2 m omega square A square. And so if we try to display this in graphical terms, say this is A point, this is B point. On y-axis, if we take the magnitude of the energy, and on the x-axis, if we take the displacement, there. At A, kinetic energy is 0, and it goes on increasing and reaches the maximum value. This is 1/2 m omega square A square. And as the particle crosses the mean position, again it goes on becoming zero. And so in this way, this is the variation of kinetic energy as the particle moves on the path AB, which is along x-axis. Then y-axis is going to represent the magnitude of kinetic energy, which will be measured in terms of joule. Now we will have a discussion about potential energy. Potential energy. Now, in order to find out the potential energy, we'll first of all find out the capacity to do the work. This capacity to do the work is going to represent the potential energy possessed by the particle. And so here in this case,